So far so good. Now I'm ready to actually quote what integration by parts tells me about I sub m. Just to prompt my memory, it's going to be uv minus the integral of v du. So it's just a bit of a straight substitution here. So let's have a go. This is a definite integral, so I'm going to put my big square brackets here. Here comes u, it's x to the m minus 1, and then v is going to be times a 12 x squared minus 1 to the power of 6. And remember what my boundaries are from the question, it's from 0 to 1. Just before I do the other half of integration by parts, you can see how this question was clearly crafted to make things kind of nice for us, right? When you put that top boundary in, remembering this is all one product, you can see in this term, this factor, 1 take away 1 gives you 0. So this whole expression, which looks disastrous, once you put in the top boundary, it's gone. Once you put in the bottom boundary, well, you've got this x term, right? So 0 to the power of m minus 1 is 0, so it's also going to come out in the wash. So that's nice, I'll just keep that in mind for later. Let's do the rest of the integration by parts. So I'm integrating now v du. So it looks to me like I've got, this is going to be a little messy, but stay with me. Here's the v. That's done, and then here comes the du, so it's m minus 1 x to the m minus 2 dx. And like I said before, this term right here, x to the m minus 2, you should recognize that, right? You're like, I needed that, it's got to come in somewhere, so this is already a really good sign, just confirming what we had before. Okay, where can we progress with this? It's sort of downhill from here. I think we've actually done the hardest part of this question, and I don't know, I wasn't part of the HSC marking back then, but I reckon anyone who got to this point, I reckon this was kind of like the 24% of people who got this question right, because the rest of it, you just have to be careful with your algebra and your calculus. So let's have a go, shall we? As explained earlier, you're just going to get 0 from the substituting in the top and the bottom boundaries there. I'm now subtracting this integral, and I do notice, if you have a look carefully, 1 over 12, that's a constant. M minus 1, also a constant in this context, because remember, I'm integrating with respect to x. So therefore, I'm just going to pull all of that out the front of the integral as my constant coefficient. So choose the right color would be helpful. M minus 1 on 12 is what happens when you put them together. I'm integrating from 0 to 1, and then I get x squared minus 1 to the 6, x to the minus 2, and you know what? I should probably put that in a more helpful order, remembering what IM was laid out for us in. You had the x term first, and then you had this x squared minus 1 stuff later. So that's all integrated with respect to x, okay? So what do I do with this? Well, I can keep on going. I still have this minus, I'll put that in brackets so I don't accidentally blend it into that fraction line there, which I have definitely done a bunch of times. Let's have a look at this expression, this integrand that we have here, right? So item number 1, you got x to the m minus 2, tick, I wanted that. But then you've got x squared minus 1 to the 6. And when you have a look back, no matter whether you got im or im minus 2 or im minus 3 or anything, right? You never get an x squared minus 1 to the power of 6. You only ever get it to the power of 5, right? That is constant, it's independent of m, like we were mentioning before. So therefore, when I look at this line, I need to break out one of those x squared minus 1s. One of those x squared minus 1s has to be factored out to leave me with an x squared minus 1 to the 5. That is going to complicate things a little bit, but there's no other way that I can get this in terms of the IM that we were given before, okay? So here's the way I'm going to do it. I'm going to call this term out the front the same. I've got this, and I'm factoring out one of the x squared minus 1s, and then I'll write this in some other colors so that we can distinguish this a little bit. I'm going to get an x squared, and then I'm going to get a minus 1. And the reason why I'm writing them separately is because I have no choice. I'm going to have to break this apart into 2 separate integrals. But that's okay. That's part of what is actually going to make the algebraic manipulation work. All right, we're on the downhill now. So I'm going to take this constant coefficient, just chuck it out the front. And then what comes inside these ridiculously large brackets? Well, I'm first going to multiply everything through by x squared. So it'll be x squared times our x term and our x squared minus 1 to the 5 term. So I'll do that in green so you can follow where that integral is. So it's 0 to 1. Now, when you multiply this by x squared, just look at the indices, right? This is index laws. So I can say I'm adding the indices together since the bases are the same. So the 2 and the minus 2, they cancel. That's convenient. So I'm just going to get x to the m, and I've got x squared minus 1 to the 5. So there you go. There's the first integral that we got from breaking that apart. And then I go again with minus 1, and everything here just comes out unchanged. So it's still from 0 to 1. That x to the m minus 2, I haven't done any weird index laws with that. X squared minus 1 to the 5 dx. And that's everything there, right? Okay, well done. How do I disentangle this, right? Well, remembering that you've got im over here on the left, right? So I can actually say, I can start to identify, being that this looks familiar, like have a look at that, compare that to the question. That looks to me like it's exactly im. And then this is the im minus 2 that we, let me scroll back up, that we wrote beforehand just so we knew where we would be able to identify it, right? So therefore, I'm going to try and simplify this out. That fraction is bothering me. I've left it there for long enough, so I'll multiply both sides by 12. There are 12 ims over there. I've got a minus m minus 1. Okay, what happens in green here? Well, we'll follow that along. That's im. And then I've got another, careful with the minus signs here, that minus is going to cancel with that minus, so I'm going to get a plus, and then you've got m minus 1 lots of, not im, but im minus 2. So I'll write that in, like so. And now I'm so close, right? You can sort of see, because you know your destination, right? Essentially what we're trying to get is im in terms of im minus 2. So we're going to make this the subject. I need to collect some like terms and all that kind of thing, and there's quite a few over here, right? So how many ims will I end up with on the left-hand side? And I mean, you can slightly cheat at this point because we're so close to the end. I'm going to add an m to both sides. So I've got, well, not an m lots of im, so I'm adding it there, so I'm going to factorize it out here, and then I'm also going to add a negative 1 lot of im to both sides. So when you add that to the 12, you're getting 11 of them. Does that 11 look suspiciously familiar? That's something that we're going to need. On the right hand side, you just have this m minus 1 on im minus 2, and I should have pointed it out earlier, but that's kind of exactly what I wanted, right? See that m minus 1 up there? So that's exactly in the right spot. I don't need to manipulate it any further. And our final line is to divide through. M minus 1, m plus 11, and you can put a nice neat bow on top of it as required. Full stop. Okay, so I hope you found that helpful. I hope it was clear, and for those of you who haven't done a recurrence relation for a while, that it was a good refresher for you.